In this video, we're going to review some very basic but very important function vocabulary. We're going to start with the definition of a function itself. F is, let's say f goes from A to B, is a function, means that for every A inside set A, there exists a unique element B inside set B with f of A equal to B. And it's important to realize that there's a lot of vocabulary that is associated with a function, and I want to just kind of go through that briefly because none of this is new to you. The set A is called the domain of the function, and that's sometimes written as domain of f. The set B is either called the target set or the codomain of f, and it can either be written as target of f or codomain of f. The range of the function is not actually equal to b. The range of the function is the set of b's inside set b such that there exists an A inside A with f of A equal to that b. The range of a function is always going to be a subset of its codomain. It's basically the set of answers. There's a couple more things that I also want to add in this vocabulary stuff. If f of little a is equal to b, then we say b is the image of a. We also say that f takes a to b. And the pre-image of B is a little bit more difficult. So let me look at that for just a minute. If we have f goes from A to B is a function, and I take any element inside the codomain B, the pre-image of little b is, let's see, let me make that more readable. The pre-image of little b is the set of things inside A such that f of A is actually equal to that b. It is a set of objects, and it is also possible for that particular set to be the empty set. There is a standard introductory way of thinking about abstract functions, which is often called arrow diagrams or cloud diagrams. So if we think about representing the domain with a blob and the codomain with a blob, if I put the elements of A over here and some elements of B over here, as long as there is no more than one arrow coming out of each one of these particular things from A, but we also have to have an arrow, this would be a function. In fact, this is a function that would be called a one-to-one function. But function means each A inside set A has exactly one outgoing arrow. So this would be another function. All three of the elements in this one are going to wind up, well, let's see, two of them go there and one of them goes here. So there's a variety of different kinds of pictures that you can draw with arrow diagrams. What I now want to do is I want to define three special types of functions that play very important roles in all kinds of mathematics. The first one that I want to look at are one-to-one functions. The formal definition of one-to-one is the following. So let's let f, going from a to b, be a function. We say f is one-to-one if and only if f has the following property. And the property that is kind of, well, I'm going to state it in two different ways. It is an implication. The first thing that I want to say is the kind of way that most people think about it when they first are introduced to this idea, which is if I take two things inside the domain, a one-to-one function is going to send those two distinctly different elements in the domain to two distinctly different elements in the codomain. In other words, if A1 is not equal to A2, then f of A1 cannot be equal to f of A2. Equivalently, we can use the contrapositive of this statement. We can say if f of A1 is equal to f of A2, this equation is an equation in set B, then we must have A1 is equal to A2 in set A. And this is nothing more than the contrapositive of the first statement. I do want to stress that in formal theoretical mathematics, this particular version of one-to-one is usually the better choice when you are trying to prove something is one-to-one. So when you're trying to prove a particular function is one-to-one. And the reason this is a better choice is that the hypothesis of this implication is very strong because it has an equal sign in it. The hypothesis of this other way of thinking about one-to-one is very weak. Knowing that two things are not equal does not give you much to go on. But when you're told that f is one-to-one, very often you want to use either of these, depending upon the circumstance. And so you need to be aware that both things are equivalent. The arrow diagram way of thinking about one-to-one looks like this. So in arrow diagrams, here's A, here's B. And basically, one-to-one says if I pick different things in A, they've got to go to different things in B. So let's see, since I have to have an outgoing on this one, I have to have at least one more thing there. Now, set B could actually have some things that did not get covered. So in an arrow diagram, f is one-to-one means for every element inside the target set B, there is no more than one incoming arrow. Well, I now want to look at another special kind of a function, and those are the onto functions. Again, I want to start with a formal definition. So f is a function. So we want f to be a function from A to B. We say f is onto B. Sometimes this is f maps A onto B. So f maps A onto B. When f has the following property. And this property is a universally quantified statement. For every element inside my codomain set B, there has to be somebody inside the set A such that f of A is equal to that particular B. Now, when we're dealing with formal mathematical proof, this particular statement gives us the usual strategy. So the strategy to prove F is onto B always starts out with pick an arbitrary element inside B and show there is always someone in set A that is sent to that arbitrary B inside set B. Let's look at the arrow diagrams for onto functions. So when we're organizing things in terms of onto functions, every one of these guys has to have at least one thing in A being sent to him. I'm going to actually send two things in there. And we're going to have So now you'll notice that we've covered every single one of the elements in B. So F is onto B in terms of arrow diagrams means every B inside set B has to have at least one incoming arrow. The final kind of function that we're going to define is something that is both one-to-one and onto. So these guys are called bijections in some textbooks. They are also called one-to-one correspondences. I typically am lazy and just call them one-to-one and onto. F is, let's get the formal definition looking a little bit better. So F goes from A to B, is a bijection or a one-to-one correspondence if and only if F is both one-to-one and onto. And the proof strategy for proving that something is a bijection is you got to do both pieces. So to prove F is a bijection, you have two proofs. So you have to prove F is one-to-one, and then you have to prove F is onto. You can swap the order if you want to, but this is two proofs. So two proofs. Order does not matter. So order does not matter. In arrow diagrams, what does a one-to-one onto function look like? In arrow diagrams, we would have A here, we would have B here, and if we are in a finite world, we are going to find out that the two sets have to have the same thing, because one-to-one says each B has no more than one incoming arrow, and onto says each B has at least one incoming arrow. So when we've got finite sets, we're going to actually wind up having A and B have the same number of things. We'll actually look at that in a little bit. But in terms of arrows, what this really means is that F is one-to-one and onto, means each B has exactly one incoming arrow. It is important to realize that a function and it can be onto and not one-to-one, and the sets can be the same. So I want to tie this video up with an interesting sort of an example that's well worth being well worth having rattling around in the back of your head. I'm going to first of all let f go from the natural numbers to the natural numbers be given by f of k is equal to k plus 1. And if I think about making two lists of the natural numbers, these lists, of course, go on and on and on forever. Actually, I'm going to need that. These lists go on and on and on forever, but the map looks like this. And it's easy to see from this kind of a setup that this f is 1-to-1 because on this bottom line, nobody gets more than one arrow, but f is not onto. And it's not onto because this guy did not have anybody coming into him. Alternatively, if I look at the next example, let's make g go from the natural numbers to the natural numbers given by, and this is going to be a piecewise function. G of 1 is going to be 1, and for k strictly bigger than 1, g of k is going to be k minus 1. If I look at g, g is going to have this kind of arrow diagram. Again, I'm going to have 1, 2, 3, 4, 5, 6, and so on. And my second copy of n is going to look like 1, 2, 3, 4, 5, 6, and so on. Actually, I think I'll put a 7 up there. The mapping is going to look like this. And it's clear from the arrows that G is onto. We don't have the same problem that we had last time, but G is not 1-to-1 because 1 has 2 incoming arrows. So for infinite sets, you can have a function be 1-to-1 and not onto. You can have a function be onto and not 1-to-1. That ends this particular video.